Hello friends, welcome to my channel. Today we'll discuss about thermodynamic properties and what are its classification. Intensive and extensive properties we will discuss, and then we'll also discuss about the properties, process and cycles. And then we'll cover the zeroth law of thermodynamics, etc. And before going in detail, I must say one thing to all of you. Please do subscribe to this channel. Of course, like it and share it. So let's start. You see, thermodynamic properties. Thermodynamic properties are the characteristics to describe the physical state of a system. So, what do you mean by this? You see, if you are a student, then you have a certain name, you have certain height, and you have a mass. So these are the characteristics to describe your these are the actually these are the characteristics to distinguish you from others. Similarly, a thermodynamic system has certain characteristics which are called the properties. For example, the pressure, volume, temperature, etc. Suppose certain amount of gas is enclosed in a piston cylinder arrangement. So it must have some suppose this is a system, and if this gas has the volume, suppose 2 meter cube, temperature suppose 30 degrees Celsius, and it has certain pressure also. So these parameters are actually known as the properties. So you can say properties are the variables to describe the state of a system. So whenever a system is at a certain state, means all the properties are defined for the system. All the properties can be defined and calculated throughout the system. If a system is at a certain state, means it must have certain pressure, it must have a volume, it must have certain temperature, it must have certain mass, it must have certain energy, every characteristic, every property can be defined, and these properties are called macroscopic because we can perceive by our senses. We can perceive these properties by our senses. That's why these properties are called macroscopic properties. These properties are divided into two types. First one is extensive properties and intensive. Extensive and intensive. So what is actually the difference between extensive and intensive? Suppose this is a system. Since this system is at a certain state, means it will all the thermodynamic properties can be defined for this system. Suppose we divide this system into two equal parts by an imaginary partition. Actually, this partition is not there physically, but this is suppose a imaginary partition. Imaginary partition. So, if initially when the system was not divided, if its volume is suppose V, mass was suppose m, before it was divided into two equal parts m, pressure was suppose P, temperature was suppose T, then what would these values assume in these parts, that we will analyze. It is obvious that since these two parts are equal, what will be the volume of this part? One would definitely know that the volume of this part is obviously V by 2. By applying common sense, we know that volume is divided into two equal parts, and this part's volume of this part will be V by 2. Mass again will be divided. But what about pressure and temperature? But pressure of this part will be P and pressure of this part will also remain same. On dividing this whole system into two equal parts, the pressure and temperature will not be divided. And temperature of this whole system was initially T, and after dividing also it will remain same. They are not changing. So these pressure and temperature are not, they are the properties that don't change with respect to the extent or size of the system. So they are called intensive properties. Pressure and temperature, they do not vary. They do not vary with size or extent of system. Before partition, the pressure was same throughout the system, that was P. After partition also it remained same in both these parts, P and P. So it is same for each and every part. Even if it is divided into four equal parts, pressure will remain same as it was in the earlier case. So that's why these pressure and temperature are called intensive properties. Intensive properties. But volume and mass, they became halved. So that's why V by 2 and M by 2, they became halved. So that's why volume and mass are the properties which depend upon the size or extent of the system. So we can define like this: extensive properties are properties related to size or extent of the system. That means when initially for the whole system mass was m, but when it was divided into two equal parts, the property value of the numerical value of the property also got changed. It became halved also. M by 2, it became M by 2, and the volume also became V. This became V by 2. So that's why these are extensive properties, which are properties related to size or extent of the system. On the other hand, intensive properties are independent of size or extent of the system. So for example, pressure, temperature, density, specific volume, etc. So you can say intensive properties are independent of the mass and extensive properties are related to mass. In this way also we can define. Usually the extensive properties are denoted by uppercase letters. But mass is an exception to this. Mass M is an exception to this. Usually the extensive properties are denoted by uppercase letters, with M being the mass being the exception. Mass is an extensive property, but it is denoted by lowercase letters m, small m. Similarly, intensive properties are denoted by lowercase letters, with pressure and temperature being the exception. They are intensive properties, but they are denoted by capital letters. Properties, when defined for unit mass of a system are known as specific properties. For example, suppose volume divided by mass is a specific volume and denoted by small v. So this is a specific property. Similarly, suppose enthalpy, total enthalpy divided by mass. Total enthalpy is denoted by uppercase letter, that is capital H, and divided by mass is denoted by small h, and this is specific enthalpy. So its unit is suppose total enthalpy is unit of total enthalpy is kilojoule and unit of mass is kg, then unit of specific enthalpy will be kilojoule per kg or joule per kg. So these are specific properties, but all specific properties, you can say all specific extensive properties are intensive property. All specific extensive properties are intensive properties. So volume, specific volume, specific enthalpy, specific entropy, all these are intensive properties. When specific term is added to any property, then it becomes an intensive property. So next is properties, process and cycle. What is this? Properties, process and cycle. So we have already discussed what is properties. Properties are the state variable of the system. When a system changes its state, means we can say that at least one property must have changed. When a system is said to be existing at a particular state means all the thermodynamic properties are defined for it and can be calculated throughout the system, and will have one value also. For entire system, pressure will have one value. You can't say that pressure can have two different values in a system. Then the system is not in a state of equilibrium. When a system is at a state of equilibrium means all the properties are defined for this state, and they will assume properties will have a unique value throughout the system. So if one property changes, then it is called a change of state. Suppose certain amount of gas is enclosed in a container and its volume is suppose 2 meter cube and temperature is suppose 20 degrees Celsius, and if it is suppose heated up, and after being heated, suppose its temperature increases or volume increases, suppose volume becomes 3 meter cube, temperature suppose remains same. Suppose if it is volume increases, then what happens? So one property just changes. That means the system is said to have undergone a change of state. So we can define a change of state. Change of state. A change of state is said to occur. Change of state is said to occur. Change of state is said to occur if at least one property changes. Even if only one property changes means you can say that the system has undergone a change of state. Suppose a system has undergone a change of state means it can be reflected on the property diagram also. Suppose this is a pressure volume diagram. So suppose this is state 1, this is suppose state 2. So that means when the system has traveled from state 1 to state 2 means its pressure has decreased and volume has increased. So on the property diagram we can understand what is the nature of the change. And so this is called a path. This is 1, 2 can be called as a process also or path. So what is path? The succession of states. Succession of states passed through, succession of states passed through during a change of state is called path. And when the path is completely specified, when the path is specified, it is called a process. Suppose we say that the path, during that path, suppose the pressure remains constant. We call it an isobaric process. Suppose during that when the system changes its state from 1 to 2, suppose its temperature remains constant. That means it is an isothermal process. So this is how we describe the path of a system, depending upon what variable changes during the path, which property changes or which property remains constant. Accordingly we can describe the nature of the path. And when the path is specified, it is called a, or you can say when the path is defined, it is called a process. So what is cycle? What is thermodynamic cycle? What is thermodynamic cycle? Suppose this is on a PV diagram. This is PV diagram. So system has traveled from state 1 to state 2 through path A, and from state 2, and then it returns back from state 2 to state 1 through path B. Now these two paths A and B constitute a thermodynamic cycle. Thermodynamic, because here the initial state and the final state that the system has traveled remains same. यहाँ से शुरू हुआ था और यहाँ ख़त्म हो गया. तो 1 से शुरू हुआ 2 तक फर्स्ट प्रोसेस में, यहाँ सिस्टम 1 से 2 तक गया, देन 2 से 1 तक आया थ्रू पाथ बी और प्रोसेस बी. So these two processes A and B constitute a cycle. So if you want to define it, you can say that thermodynamic cycle can be defined as a series of state changes such that final state such that the final state is identical with initial state. So you see, thermodynamic cycle can be defined as a series of state changes such that the final state is identical with the initial state. In this case, there are two paths in a cycle. In some cases, there may be 3 paths or 4 paths, like Carnot cycle, which we will study later on, will consist of 4 processes. So minimum 2 processes are required to constitute a thermodynamic cycle when a system's initial state and final state remain same. But this is not a cycle. Suppose one would argue that here initial state is suppose 1, this is 2, and reversible path, again on 2, 1 it will come back to initial state. This is not a cycle. So if a path is reversible, then the system can again move from the final state to initial state, but that does not mean that this path and its reversible path cannot constitute a cycle. So this is a cycle, but this is not a cycle. At least 2 processes should be there to constitute a cycle. That means suppose a system, if heated, its temperature increases. Suppose a system was initially at 20 degrees Celsius in thermal equilibrium with the surrounding, and if it is heated, then its temperature will increase. After some time, suppose the system is allowed to cool down, and that heat is removed, then the system will be, if the system is allowed to cool down and eventually it comes in thermal equilibrium with the surrounding, means it will again attain that same temperature. So that means the system has completed a thermodynamic cycle. So whenever a thermodynamic system is in a state of equilibrium, we will come in detail about equilibrium, what is thermodynamic equilibrium, and at least at this point of time we can say that when a system is in thermodynamic equilibrium, means all the properties can be defined for it. So when a system is in equilibrium, means all the macroscopic properties can be defined for it, but it is not necessary to know or to specify all the properties, all the macroscopic properties, volume, temperature, pressure, many more properties are there. All the properties should not be specified to fix the state of a system, because if some properties are specified, then other properties can be calculated because they assume some values. Once we know certain number of values for a thermodynamic system which is at an equilibrium state, then other values assume some values, certain values automatically. So that's why we have to know how many number of properties are required to fix the state of a system, and that is given by the state postulate. The state postulate says that a state postulate describes about the number of properties required to fix the state of a system, so that out of those number of properties, minimum number of properties, we can calculate all other thermodynamic properties. This postulate states that the state of a simple compressible system is completely specified by two independent intensive properties. Two independent intensive properties. So this is what the state postulate states. The state of a simple compressible system is completely specified by two independent intensive properties. So what is this simple compressible system? A simple compressible system is one in which the simple compressible system is one in which there is no electrical, magnetic, motion, gravitational and surface tension effects. And you know, these effects are due to external force fields, and most of the engineering systems, these effects are absent. So that's why most of the engineering systems can be defined as simple compressible system. So for complete specification of a simple compressible system, two properties, independent properties and intensive properties, are required. Independent properties means one property can be changed without changing the other. Independent properties mean one property can be changed without changing the other. So if suppose any of these most effects is present, then an additional variable is needed, additional properties is required. Suppose in a system, suppose gravitational effect is present, that means another variable z, the height from the datum level, is required for a complete specification of a system. So there is also a Gibbs phase rule which also relates to this calculation, and which is independent variables. That rule says that component minus phases plus 2. Phases plus 2. You know, for most of the simple compressible system, temperature and specific volume are independent properties, but temperature and pressure are not independent for most of the systems. They can be independent for single phase system, but for a double phase system, like when the liquid and vapor are in equilibrium, the temperature and pressure are not independent, because for every temperature there is a pressure, saturation pressure. Suppose 100 degrees Celsius is the boiling point of water at standard atmospheric pressure, but if you go to the mountain top, then the boiling point decreases because the pressure there is less than the standard atmospheric pressure that exists on the surface of the earth. So that's why this can also be derived from this equation also, which we will cover later on.